You ever run into a problem that just stops you in your tracks? You know the kind where adding just one more little thing to the mix suddenly makes it take twice as long to solve? Well, today, we're going to talk about a brilliant little trick to smash right through those kinds of exponential walls. It's called meet in the middle.
First, take a look at this number, over 1 trillion. Just let that sink in for a second. What do you think that is? It's not the number of stars in the galaxy, nope. It's actually something much, much closer to home for anyone who writes code.
That's right. If you have a problem with just 40 items, and for each one you can either pick it or not, a simple brute force check would have to run through over 1 trillion possibilities. This, my friends, is what we call the exponential wall. It's what makes a lot of really interesting problems basically impossible to solve head-on. At least not in our lifetime.
Look, you can't just throw more servers or a faster processor at a problem like this. It won't even make a dent. You have to be smarter. You have to outthink the problem itself. So, how in the world do we do that?
Well, the answer is a wonderfully clever technique, and it's called meet in the middle. Honestly, it's less of a rigid algorithm and more of a beautiful insight that completely changes the game. So here's the big idea, and it's surprisingly simple. Instead of trying to solve one massive, impossible exponential problem, you just split it in half. What you're left with are two way smaller problems. You solve each of those halves on their own, and then, and this is the secret sauce, you find a really slick, efficient way to combine their answers to get your final solution.
Think of it like this. Imagine you have to find a route from one side of a country to the other. That's a huge search space, right? But what if you just split the country down the middle? You could figure out all the roads that lead out of the western half and all the roads that lead into the eastern half. Then all you got to do is find where those roads connect at the border. It's a much smarter way to search. And this isn't some brand new idea either. It has a really solid history. The core concept was used way back in the 70s to break cryptographic codes, and then it was formally written up for classic computer science problems like subset sum. So yeah, it's a proven, powerful tool you really want in your toolbox.
All right, so enough theory. Let's get our hands dirty and see how this clever idea actually works in practice. We're going to use the classic subset sum problem as our guide. The question is simple. Given a list of numbers, can we find some combination of them that adds up to a specific target number?
So the whole process really breaks down into 4 straightforward steps. First, you take your list of numbers and just chop it right down the middle. Easy enough. Second, you generate every single possible sum you can make from the left half, and you do the exact same thing for the right half. Third, and this is super important for speed, you sort one of those lists of sums. And finally, step 4, this is the meeting part. For every single sum from the left list, you do a quick search in the right list to see if its missing piece is there.
Let's make this real. Say our array is 3, 1, 4, 2, 2. We split it into a left half, 3, 1, and a right half, 4, 2, 2. For the left side, the possible sums we can make are 0 from picking nothing, 1, 3, and 4 from picking both. We do the same for the right side, and you can see all the sums we get there. Now we have our 2 little universes of possible sums.
And here's the magic. This is where we meet in the middle. Let's say our target sum is 6. We'll grab a sum from our left list. How about 4? Now we ask, what's its complement? Well, 6 minus 4 is 2. So we need to know, is there a 2 in our right sums list? And because we sorted that list, we can use a lightning-fast binary search to find out. And, yep, it's there. Boom, we found a solution. Okay, this all sounds pretty neat, but what's the actual payoff? What do we gain? And more importantly, what's the catch? Let's talk performance and the trade-offs that come with this technique.
So this is where it gets really exciting. A brute force solution, as we saw, is O to the 2 to the n. But meet in the middle, its time complexity is roughly O to the 2 to the power of n times 2 divided by 2. That little division up in the exponent, it's a complete game changer. For that problem with 40 items, we just went from over 1 trillion operations down to around 1 million. We went from literally impossible to totally doable.
I mean, just look at the difference. It's staggering. While the brute force approach just skyrockets off into infinity, meet in the middle stays pretty manageable for much larger problems. It turns the impossible into just, well, merely challenging.
But of course, there is no such thing as a free lunch in computer science. To get this incredible speed up, you have to pay a price. And that price is memory. Remember how we had to generate and store all those sums for both halves? That's the trade-off. It requires O of 2 to the n over 2 space, which can be a lot.
Now this is a really key point. You might be thinking, hey, what about dynamic programming? Great question. When do you use which one? It all comes down to the constraints of the problem. If your target value, let's call it W, is pretty small, DP is often the better choice. It's faster and uses less memory. But if that target value is huge and your number of items, N, is moderate, say around 40 or 50, then meet in the middle is absolutely your hero.
So, how can you take all this knowledge and use it to really shine in a technical interview? Let's put together your game plan. Okay, so when you see a problem like this in an interview, here is your playbook. First, always start by mentioning the brute force solution. It shows you understand the baseline complexity. Then, you swoop in and propose meet in the middle, and you state that improved complexity. But, and this is crucial, you immediately follow up by discussing the space trade-off. That shows you're thinking about the real-world constraints. And for bonus points, you can mention how versatile it is and compare it to DP.
Knowing what not to say is just as important. Avoid making absolute statements like, oh, meet in the middle is always better than DP. It's just not true. Don't try to downplay the memory cost. It is significant and you should acknowledge it. And finally, remember that this technique is super flexible. It's not just for finding if a sum exists, you can adapt it to count how many solutions exist, or even to find the solution that's closest to the target.
So here's the real takeaway. The next time you're staring down an exponential problem, a problem that seems totally impossible, I want you to ask yourself one simple question. Can I split this problem in half? That question is the key to unlocking this whole way of thinking. It's how you can turn impossible problems into elegant, clever solutions. So what impossible problem are you going to split in half next?